Hi everyone. In this lecture we're going to be talking about gradient descent and optimizers. And so you most likely already know these things. So this is mostly just a recap of things that you may be familiar with. But more specifically, we're going to mention a few things which are more relevant for the deep learning scenario. So what is optimization? By optimization, we typically mean the task of, in machine learning and in deep learning specifically, the task of minimizing the objective function parameterized by the model parameters. So we will typically denote this function with these parameters as j of w. And w here are the model parameters, the vector which contains all the model parameters. Another common notation for these parameters is also theta. You will see that in other slides and lectures often. So keep in mind that usually these are the two most common symbols for that. So what an optimization algorithm is attempting to do is to find either the global minimum of the cost function, and that is the case for so-called convex optimization, where the objective function has a one single global minimum, typically some kind of a bowl-shaped function. But in the context of deep learning, where we do not have this property, we will just try to find the lowest possible value of the objective function within some local neighborhood. Since as I just mentioned, in the normal case, the objective function is not going to be convex, so we're just doing some local search in this case. And so the most common approach for optimization is going to be based on this general concept called gradient descent. And just as a reminder, what gradient descent does is to move the parameters in the direction which decreases the value of the objective function. So that is going to be the direction opposite to the gradient of that function with respect to the parameters. And so this is what the update would looks like. The parameters at time t are going to be updated with respect to the parameters at the previous time by subtracting the gradient, which is indicated by this inverted triangle symbol multiplied by this coefficient eta, which is known as the learning rate. Okay, so just a recap of what this notation means. W are model parameters. This is going to be a vector. Eta is a learning rate, and that's a scalar typically. This symbol called nabla, the triangle, is a gradient. J is the loss function, or more generally in optimization, some kind of objective function that we're trying to optimize. So one thing which is important in order to make sense of this notation is that J, this objective or loss function, in order to calculate it, you need to use the data, the training data such as X and Y. And so, but in this notation, we just denote it as J of W and not, for example, J of W, X and Y, even though these are also inputs to that function. And that is because we are in this particular context of optimization, we are interested in how the value of this function j changes with w, because that's what we're going to be updating. We're going to be updating w. X and y, so these our data, our training data is just constant, so we will not be obviously changing it. But just keep that in mind that it's kind of a bit of a simplified notation here. So what types of gradient descent are there? So in general, the most classical version of gradient descent is sometimes called batch gradient descent, and that is where we calculate j for the whole data set. So we have the exact gradient of this function, And after doing that, we make an update to the parameters and recalculate it again with the new parameters, again over the whole data set, and so on. Then there is stochastic gradient descent, and that typically refers to the extreme case where we calculate the value of the objective function for a single data point, so for a single trading example, then make an update to the parameters. So that's the kind of canonical meaning of stochastic gradient descent. Of course, in practice, we typically use something which is in between these two cases, namely mini-batch gradient descent. And in this case, what we do, we calculate the objective function for a sample of k data points, then make an update to the parameters, and then again take another sample of k data points, and so on. So typical values of k in deep learning would be something like 32, 64, up to something like 512 or so. So this is mostly just determined by how many of these samples fit in your GPU memory, and so the more you can put in the GPU memory, the better, because this algorithm work faster. So this type of gradient descent, mini batch gradient descent, is the usual choice in deep learning. That's almost always what we use. One thing which is worth mentioning, that informally we often refer to stochastic gradient descent. We actually mean mini batch gradient descent. So just these are not like super strict. This terminology is not super strict in this regard, but keep in mind that there are these three different kind of points in this spectrum. And so one more thing to also remind you about the difference between the behavior of gradient descent versus stochastic gradient descent is what the trajectory in parameter space looks like. So in this picture on the right hand side, what you have is some parameter space, two-dimensional, so corresponding to having just two parameters, and you can see the black arrows and the points correspond to the updates, and which give this smooth trajectory for the case of gradient descent, and then the red arrows and the points correspond to the more erratic trajectory that we have with stochastic gradient descent. So why is this trajectory more erratic? Well, the reason for this is that we are updating after each training example, or after a few in the case of mini batch, and so our estimate of the gradient of the objective function is noisy, in the sense that we're not using the whole data set for that. We're only using some relatively small sample of the data set, and so we don't know what the true gradient is of what the true gradient would be on the complete data set. We do know what it is on this small batch, and so we just take it and go with it and do this update. But it means that it's moving quite erratically. That is not something that we necessarily need to worry a lot about. To some extent, this will just average out in the long run. It will make the number of steps needed to get to some reasonable point in the parameter space longer, but it may also have the effect of regularization. So a lot of the cases where we add some kind of noise to the training or to the data, or to something about how we do deep learning, that actually improve generalization. And with stochastic gradient descent, there is also some of that effect. However, like an extremely erratic behavior is not desirable, and so we will also look at some ways of dampening it a bit. And so this update formula that we saw, this basic formula can be modified to improve optimization, the behavior of this trajectory. For example, smoothing it somewhat, as I just mentioned. One other thing, which is also a little bit tricky with this update formula, is that relies on the learning rate, and the learning rate can be quite difficult to tune. It can be quite tricky to tune it, depending on every specific data set and model. it will be different, and so that is something that is making working with these models more difficult than it should be. And we will also might want to allow the learning rate to vary per parameter rather than having a single global learning rate which we're using for all the parameters. The parameters may, some of them may need larger updates than others, and so we may want to do that, allow that. So keep in mind that there is many different variants of optimizers. There is a whole zoo of them, and in this short lecture, I will only mention a couple of examples for illustration. So the first thing I wanted to mention is the concept of exponentially weighted average. This is a concept which we will be using in the rest of the lecture. And so idea is that if you have some time series like the data depicted in this plot on the right hand side of the slide in blue, often this time series may contain some type of noise or some variation which may obscure the overall pattern of the overall trend that this data should be displaying, or that we think there is some underlying pattern in this data, and there is some local small scale noise which is making it difficult to see. And so we may want to smooth this type of data to make this overall trend more obvious, and we can do that by averaging over a window of preceding values. And so one way of doing that is to use this formula, which is known as exponentially weighted average. We have this parameter beta, which you can use to control how large this window is over which we are averaging. So basically what we're going to do with the value v, the smoothed value v at the current point in time t, is going to be a sum of the previous, or weighted sum of the previous value of the previous smoothed value and the original value at the current point in time. And the weights are given by beta and 1 minus beta here. And by increasing beta, we can control how long the window over which we are averaging is going to be. And so one thing we can do with this, using this exponentially weighted average, is to smooth the trajectory in the weight space for stochastic gradient descent. And that is known, this approach is known as momentum because of some analogies or some analogies to the behavior of physical objects, but I will not go into that. It is a relatively simple application of this exponentially weighted averaging to simply to smooth the updates that we're doing. And so this is the formula that we see here. We're going to compute this update term v, and that is where the averaging comes in. So we are summing two components. The first one is v, the previous value of v weighted by beta, and the second component is the value of the current gradient of our objective function weighted by 1 minus beta. So this is the update term, and then in the second line we just update the weights using this update term multiplied by the learning rate. So this is momentum. What this achieves is that the erratic nature of stochastic gradient descent becomes less erratic. It is smoothed out, so this trajectory doesn't jump around so much. It's moving in a more straightforward manner in practice. Another change to the update formula that I wanted to discuss is known as RMS-prop. So RMS-prop is stands for root mean square propagation, and it was introduced actually not in a paper but in lecture slides by Jeff Hinton in the Coursera course. So you can check these slides if you want to know all the gory details. But the general idea here is that we will adapt learning rates or the amount of update per weight by dividing updates by the root mean square of the gradient, and this root mean square we just keep it we compute the mean by moving average by this exponentially weighted average approach. So this is again what is shown here in these formula. We have this term ST, where T stands for the current point in time, and it's a combination of two things. The first one is the previous value of ST, but weighted by beta, and the second component is the square of the gradient of the objective function weighted by 1 minus beta. So then what we do in the second part of the formula is that in addition to multiplying the gradient by the global learning rate eta, we also do a element-wise multiplication of this gradient by 1 over the square root of this term s that we computed in the previous line. Okay, so this circle with the dot simply denotes a element-wise multiplication. So we are multiplying each element in the gradient by each of these inverse square roots.